Right now in your kitchen, there is an object you used this morning. You used it to clean. You ran hot water over it, worked it into a lather, and scrubbed the surfaces that your food touches. You did this in the sincere belief that you were making things cleaner. A study published on June 1st, 2026 in the peer-reviewed journal Environmental Advances by a team at the University of Bonn has something specific to say about that object. Not a theory, not a computer model, a direct measurement. The study found that a standard polyurethane kitchen sponge releases microplastic particles into your sink water every single time it is used, not occasionally, every time. The team calculated that across all households in Germany alone, this adds up to hundreds of tons of microplastics entering wastewater systems annually. From sponges, from the thing you use to get your dishes clean. Here is what makes that number land differently than the usual microplastics headlines. This is not plastic leaching from a water bottle you leave in the sun. This is not a packaging contaminant from a food manufacturer. This is physical degradation happening in your hands, in your sink, in the 12 inches of warm water between you and your plate. And it is happening because of friction, because of the act of cleaning itself. I want to walk you through exactly what this study found, what it tells us about how these particles enter the body, and what the broader science says is happening when they do. Because the University of Bonn study did not arrive in isolation, it arrived in the middle of a year in which the science on microplastics has accelerated faster than at any prior point. There is a reason this matters right now, in the first half of 2026, that it did not quite matter in the same way in 2024. And I will explain that reason before this video is done. Before we go into the science, here is what this video is going to deliver. First, the specific findings of the Bonn study, including what they actually measured and how they measured it, because the methodology here is more important than the headline number. Second, what polyurethane foam is at the molecular level and why it degrades the way it does. Third, what the 2024 New England Journal of Medicine study found when it looked at microplastics in human arterial plaque, and why that finding changed the conversation at the institutional level. Fourth, the 3 biological routes by which microplastic particles enter the body from a kitchen context. And fifth, 6 specific practical changes you can make to your kitchen routine, none of which require throwing everything out and starting over. I cover the science of what everyday household chemicals, materials, and substances do to the human body and brain. I am not a physician, and nothing in this video is medical advice. What I do is read the peer-reviewed literature carefully, translate it into plain language, and explain the biological mechanisms as clearly as the current evidence allows. The University of Bonn study was not trying to make headlines. It was trying to answer a specific, unglamorous question. How much microplastic material does a standard kitchen sponge shed per washing cycle, and where does that material go? To answer it, the researchers set up a controlled washing protocol. They used standard polyurethane foam sponges, the kind you would find in any supermarket. They ran a measured number of washing cycles under standardized conditions of temperature, pressure, and duration. After each cycle, they collected the water and filtered it to isolate particles of a specific size range. Then they counted. The results were not ambiguous. Each washing cycle released measurable quantities of microplastic fibers and fragments from the sponge itself. The particles ranged in size from several hundred micrometers down to fragments small enough to classify as nanoplastics. The smaller end of that range is the more biologically relevant end, as I will explain shortly. When the researchers extrapolated these per-cycle measurements to total household sponge usage across Germany, they arrived at a figure in the hundreds of tons per year. That is a significant number for a single product category, and Germany is one country. The mechanism behind this is straightforward once you understand what a polyurethane foam sponge actually is. Polyurethane is a polymer. It is made by cross-linking long molecular chains under controlled conditions to create a material with a specific cellular structure, a lattice of interconnected air pockets that makes it absorbent and flexible. That structure is excellent for cleaning. It is also, under repeated mechanical stress combined with heat and alkaline detergents, subject to progressive degradation. Every time you scrub with a sponge, you are creating friction between the foam matrix and the surface you are cleaning. Over time, and in some cases very quickly, that friction breaks the polymer chains at their weakest cross-linking points. Small pieces detach. Some of those pieces are large enough to see if you look closely. Many are not. And the water you are using to rinse the dishes carries those fragments directly onto the surfaces your food touches. This is the part of the mechanism that does not appear in most coverage of this study. It is not only about what goes down the drain. Some of it stays. Some of it lands on the plate, on the glass, on the cutting board. The study measured what leaves the sponge. The implication for what arrives on your dinnerware is one the researchers raised explicitly in their discussion section. The University of Bonn study would have been interesting in 2022. In 2026, it is part of a convergence. In March of 2024, the New England Journal of Medicine published a study that marked something of a threshold in the microplastics literature. The research team collected samples from carotid artery plaques removed from patients undergoing surgery. They were looking for something specific. They found it. Microplastic and nanoplastic particles were present in the arterial plaque of the majority of patients studied. The patients with detectable microplastics in their plaque had a measurably higher rate of heart attack, stroke, and death over the following 34 months than patients without detectable microplastics. I want to be careful with that finding because a correlation in a clinical study is not the same thing as a proven causal mechanism. The researchers were explicit about this. What the study established is that microplastics are reaching the arterial wall in humans, that they are accumulating there in a way that can be measured, and that the presence of this accumulation is associated with worse cardiovascular outcomes. But here is why this matters for our sponge conversation. The particles that the Bonn study identified at the smaller end of the size distribution are specifically the particles most capable of crossing biological barriers: the gastrointestinal lining, the respiratory epithelium. In the case of the very smallest nanoplastic fragments, potentially the blood-brain barrier. This is not speculation. It is documented in the literature on nanoplastic translocation, and it is the reason the United States Environmental Protection Agency opened public comment on microplastics in drinking water in June of 2026, and why a $144 million research program called STOM, funded through ARPA-H, launched this year specifically to quantify microplastic exposure across everyday products. The science is converging, not around a single alarming conclusion, but around a body of evidence that is becoming difficult for public health institutions to continue treating as peripheral. Understanding how microplastics from a kitchen sponge could realistically enter the body requires distinguishing between three different exposure routes because they are not equally well understood and they do not carry the same level of concern. The first route is ingestion. When microplastic particles land on a rinsed dish or glass, any food or liquid placed on that surface can carry them into the digestive system. The gastrointestinal tract is the most studied route for microplastic accumulation in humans. Particles have been detected in stool samples, in liver tissue, in colon tissue, and in the arterial plaques I described a moment ago. The evidence for this route is the most direct. The second route is inhalation. Polyurethane foam degradation does not only produce particles suspended in water, it also produces airborne fibers. In an enclosed kitchen environment, where hot water accelerates particle release and ventilation may be limited, some fraction of the fibers shed during dishwashing become airborne. Microplastics have been found in human lung tissue. The concentrations observed in lungs suggest ongoing inhalation as a route, though the relative contribution of kitchen activity specifically is not yet quantified. The third route is dermal absorption, and this is the most contested of the three. The skin is an effective barrier for many substances. For large microplastic fragments, the dermal route is probably not significant. For nanoplastic particles, the evidence is more complicated. Some studies have demonstrated penetration of the outer skin layers by particles in the nanometer size range under conditions of mechanical friction, which is precisely the condition involved in scrubbing dishes. This is the least settled area of the science, and I do not want to overstate it. What I will say is that it is an area of active investigation for exactly this reason. What all three routes share is that the kitchen sponge is not a passive object in this picture. It is a source, a degrading polymer source that you interact with in warm water with your bare hands multiple times a day. None of this requires a panic. It requires a relatively small number of deliberate changes to a routine most people have never had a reason to examine. The first change is the most impactful. Replace your polyurethane foam sponge with a non-synthetic alternative. Natural loofah, wood pulp cellulose sponges, and cotton-based cleaning cloths do not have the polymer cross-linking structure that makes polyurethane foam a microplastic source under mechanical stress. They degrade, but they degrade into organic material, not synthetic polymer fragments. The second change addresses the scrubbing function specifically. If you use a sponge primarily for scrubbing, a natural bristle brush made from plant-based fibers achieves the same mechanical function without the polymer degradation. Wooden-handled dish brushes with sisal or agave bristles last considerably longer than a standard sponge before needing replacement. The third change is about rinsing protocol. Whatever you use to clean your dishes, a thorough final rinse with clean running water, allowing water to flow over each surface for several seconds, removes a significant fraction of particles that would otherwise remain on the surface. This costs nothing to implement and takes approximately 10 additional seconds per dish. The fourth change is ventilation. If you are washing dishes in a small kitchen, opening a window or running a kitchen fan during washing reduces the airborne fraction of any particles released. This applies not only to sponge use, but to any cleaning activity that generates airborne particulates. The fifth change is about sponge life cycle. If you do continue to use a polyurethane sponge, replacing it every 5 to 7 days, rather than every 2 to 3 weeks, significantly reduces cumulative degradation and particle release. The Bonn study found that particle release increases as the sponge ages, and the polymer structure becomes more degraded. A fresher sponge releases fewer particles. The sixth change is about storage. A wet sponge that is compressed while drying accelerates degradation at the compression points. Storing your sponge in a way that allows it to dry without compression on a rack or holder with airflow extends the structural integrity of the polymer matrix and reduces the rate of degradation between uses. Here is something the news coverage of this study has largely not mentioned. The researchers made a specific observation about sponge age that has a direct implication for how you think about the sponge you have right now. They found that the rate of particle release was not constant across the sponge's life cycle. It was lowest in the first few uses, increased significantly between uses 5 and 15, and then leveled off at a higher plateau that persisted until the sponge was structurally failing. In practical terms, this means that the sponge you bought 3 weeks ago is currently releasing more particles per wash than the sponge you bought 3 days ago, and both of them are releasing more than they did on the first use. The practical implication is that the standard advice to replace your sponge frequently is correct, but the reason that advice is usually given, which is bacterial contamination, understates the case. There is a second, independent reason to replace frequently, which is the polymer degradation curve. A sponge that smells fine and looks intact may be at the peak of its degradation release rate. If you take one physical action based on this video today, take this one. Walk to your sink, look at the sponge. If it is more than 2 weeks old, replace it before your next dishwashing session, and replace it with one of the non-synthetic alternatives I described. The kitchen sponge is not going to be the last object in your home that turns out to be more chemically or physically active than its appearance suggests. That is, in some ways, the consistent discovery of environmental health science over the past 2 decades. The materials we chose for their convenience and their apparent inertness are, under the conditions of daily use, not as inert as we assumed. The University of Bonn study is not a catastrophe. No single study is. What it is, in the context of the New England Journal of Medicine cardiovascular findings, the EPA's formal engagement with the issue, and the ARPA-H funding commitment, is a data point that now has a great deal of company. The conversation has shifted from whether microplastics accumulate in human tissue to what that accumulation means, and at what exposure levels effects become clinically significant. What you can do in the meantime is make the changes I described. They are not expensive, they are not extreme. They are simply a response to what the current evidence suggests is a reasonable precaution. And they are changes you can make today. If this kind of science-based analysis of the everyday environment is what you want more of, subscribing to this channel is the most direct way to get it. Each video takes one ordinary object or substance and works through the biology and chemistry as clearly as the published evidence allows. The goal is not alarm, the goal is understanding. I will see you in the next video.